Every image the James Webb Space Telescope captures of the earliest universe contains something unexpected. Small, intensely bright, deeply red points of light scattered across the cosmos as it existed less than 1 billion years after the Big Bang. They appear in survey after survey. They are everywhere in that ancient era. And then, roughly 1.5 billion years after the Big Bang, they simply stop appearing. Completely. Gone. These objects, now widely known as little red dots, do not fit into any established category of cosmic structure. They are not behaving like galaxies. They are not behaving like black holes. They are denser than they should be, brighter than they should be, and redder than distance alone can explain. Astronomers who have devoted years to understanding the early universe are now confronting a serious possibility that these objects represent a form of cosmic body that has never been directly observed before. Something that is, in a very literal sense, part star and part black hole simultaneously. Understanding what these objects are matters far beyond the mystery itself. The early universe is not just interesting history. It is the origin point of everything we see today, every galaxy, every star, every atom in your body. If something was happening in that first billion years that we did not predict and cannot currently explain, then our foundational models of how the universe grew and evolved may be missing something significant. Little red dots may be the observational evidence that fills one of the deepest gaps in modern astrophysics. To appreciate why these objects are so puzzling, it helps to understand what the early universe was supposed to look like. In the standard model of cosmic evolution, the universe began as an extraordinarily hot, dense state, approximately 13.8 billion years ago. As it expanded and cooled, matter began to clump together under gravity, forming the first stars roughly a few 100 million years in. Those early stars were massive, short-lived, and eventually exploded, seeding their surroundings with heavier elements and the raw material for the next generation of stars and eventually galaxies. Black holes formed from the remnants of the most massive stars, and over billions of years, the small black holes at the centers of galaxies fed on surrounding gas, gradually growing more massive. This is a slow process, a careful step-by-step construction project that spans billions of years. According to our best models, the black holes at the centers of galaxies should have been quite modest in size during the first billion years of cosmic history, and the galaxies themselves should have been relatively small, irregular, and still actively building their stellar populations. That is what the models predict. That is what we expected to find when we looked back far enough. What we actually found was something else entirely. The James Webb Space Telescope launched on the 25th of December, 2021. It was the product of decades of engineering effort, designed specifically to observe the universe in wavelengths of light that previous instruments could not access. Its primary mission was to peer back into the epoch of the first galaxies, the cosmic dawn when the universe was young and chaotic and full of firsts. What astronomers did not anticipate was that nearly every image of that era would contain the same baffling anomaly. The little red dots were first catalogued in data from 2 observational surveys called Aegir and Fresco. These were programs designed to hunt for galaxies at extreme distances, probing the universe as it existed between 500 million and 1 billion years after the Big Bang. As Webb's data came back, researchers noticed unusual objects appearing again and again. Compact, bright, and strikingly red, they were present across the sky in astonishing numbers. By 600 million years after the Big Bang, the early universe appears to have been populated with them. Their properties were formally described and categorized in a paper published in March 2024, authored by Jorrit Matthey of the Institute of Science and Technology in Austria. What that paper established confirmed what early observations had hinted at. These were not ordinary objects, and they did not fit the established categories. The first unusual feature is their size. Little red dots are extremely compact, typically no more than 500 light-years across. For comparison, the Milky Way spans roughly 100,000 light-years. These objects are approximately 200 times smaller than a typical galaxy. Yet despite being so tiny, they shine with the intensity of much larger structures. Their luminosity is difficult to reconcile with their size under any conventional model. The second feature is their color. They are deeply, emphatically red. And while objects at extreme distances are expected to appear red due to the cosmological redshift of their light, the redness of little red dots goes beyond what redshift alone can produce. When astronomers broke their light apart using spectroscopic instruments, the spectrum told a complicated story. The color was not simply the result of distance. Something else was making these objects red. The first hypothesis was dust. This is a natural place to start. Dust grains in space preferentially scatter shorter, bluer wavelengths of light while allowing longer, redder wavelengths to pass through relatively undisturbed. It is the same physical principle that turns the sun orange and red near the horizon, when its light has to travel through more of Earth's atmosphere. If little red dots were embedded in thick clouds of cosmic dust, the dust would absorb and scatter their blue light, leaving only the red behind. It seemed like a reasonable explanation. Then the mathematics refused to cooperate. Dust in galaxies is produced primarily by stars. There is a well-established and consistently observed relationship between the number of stars in a galaxy and the amount of dust those stars generate over their lifetimes. In late 2024, a team led by Caitlin Casey at the University of Texas in Austin calculated how much dust would be needed to explain the redness of little red dots, then compared that to the dust predicted by the stellar population suggested by the optical light from those same objects. The result was striking. The stellar population implied by the observed light could account for only approximately 1% of the dust required to explain the redness. The shortfall was 2 orders of magnitude. 2 orders of magnitude in science is not a rounding error. It is a fundamental discrepancy. It meant one of 2 things. Either the models of dust formation in early galaxies are substantially wrong, or the primary light source in little red dots is not stars. This naturally led to the second hypothesis. Perhaps these objects were not galaxies at all. Perhaps they were powered by something at their centers. At the core of most large galaxies sits a supermassive black hole. When these black holes are actively consuming gas and dust, the material forms a spiraling disk around the black hole called an accretion disk. The gas in this disk gets compressed and heated to extraordinary temperatures, sometimes exceeding 12 million degrees Celsius, and it radiates brilliantly across a wide range of wavelengths. Active galactic nuclei, as these systems are called, are among the brightest persistent objects in the universe. Surrounding a typical active black hole is a structure called a torus, a ring of gas and dust shaped roughly like a donut that encircles the accretion disk at a greater distance. When a black hole is viewed from the side, this torus sits between the observer and the bright central source. The dust in the torus absorbs shorter wavelengths and transmits longer, redder ones. This would produce exactly the kind of redness seen in little red dots, and it would explain their brightness, since active black holes can outshine entire galaxies. It would explain their compact appearance, since the light would be dominated by the single bright central source. And it would explain why they appeared as simple points of light, rather than resolved structures with visible internal features. The spectral data added more support to this interpretation. Little red dots show broad emission lines in their spectra. Emission lines are produced when gas emits light at specific wavelengths, corresponding to the energy transitions of particular elements. When gas is orbiting a massive central object at high velocity, the Doppler effect broadens these lines. Because some of the gas is moving toward the observer and some is moving away, which shifts the wavelengths in opposite directions and spreads the line out into a wide peak. The broader the line, the faster the orbital velocity, and the faster the orbital velocity, the more massive the central object must be. The emission lines in little red dots are extremely broad, which pointed strongly toward very massive black holes. But then another measurement made the black hole theory complicated. When astronomers looked for X-rays coming from little red dots, they found none. This was a major problem. Active black holes are almost universally associated with X-ray emission. The hot inner regions of the accretion disk produce copious X-rays, and in any known active galactic nucleus, they are present. The complete absence of X-ray emission from little red dots was an uncomfortable mismatch. And there was a second issue. In the local universe, the relationship between a black hole's mass and the mass of its host galaxy is remarkably consistent. Black holes typically account for about 0.1% of the total mass of the galaxy around them. This is not a coincidence. It reflects a co-evolutionary relationship, in which the growth of the black hole and the growth of the surrounding galaxy regulate each other through feedback mechanisms that are not yet fully understood, but which consistently maintain this ratio. When researchers estimated the black hole masses in little red dots from the broad emission lines and compared them to the host galaxy masses, the ratio was far off. Black holes in little red dots appeared to make up closer to 10% of their host galaxy's mass, not 0.1%. 10%. The black holes looked 100 times too massive for the galaxies surrounding them. Either the black holes had somehow grown to full size before the galaxy had time to develop, or the mass estimates were being significantly distorted by something in the physics of the system itself. Fabio Pacucci, an astrophysicist at the Harvard-Smithsonian Center for Astrophysics, framed the dilemma clearly. If little red dots contain black holes, those black holes are enormously oversized relative to their galaxies. But if they contain only stars, the stellar densities required to produce their brightness would be physically unsustainable. Stars packed that closely together would undergo constant collisions and mergers, and the gravitational dynamics of such a system would be wildly unstable. Neither the star-filled galaxy model nor the active black hole model could fully account for all the observed properties simultaneously. Something new was needed. Anna de Graaf is an astrophysicist at the Center for Astrophysics, Harvard and Smithsonian, with a specific focus on the most extreme objects in the early universe, the objects that fall furthest from expected distributions and resist classification. She designed a new observational survey to hunt for precisely these objects. The program was called the Red Unknowns, Bright Infrared Extragalactic Survey, abbreviated as RUBIES. During 2024, de Graaf's team used nearly 60 hours of Webb observing time to obtain detailed spectra for 300 red objects in the distant universe. Of those, they estimated between 30 and 50 were genuine little red dots. Published in March 2025, it became the largest spectroscopic sample of these objects ever assembled at that time, covering a range from 650 million to 1.5 billion years after the Big Bang. The results did not simplify the picture. They made it considerably more complex. The RUBIES survey revealed that the population of bright red objects in the early universe is substantially more diverse than anyone had anticipated. Even objects that appeared similar in imaging data showed dramatically different spectral signatures when analyzed in detail. Some were dusty star-forming galaxies, consistent with relatively conventional models of early galaxy evolution. Some appeared to be galaxies that had already stopped forming stars at surprisingly early times, which is itself an interesting and not fully explained observation. And some showed all the spectral hallmarks of active black holes at the centers of young galaxies. This suggested that both camps in the debate, those favoring starburst galaxies and those favoring active black holes, were each partially correct. The category of little red dot had been grouping together objects that were actually quite different from one another. But within the RUBIES sample, there remained a subset of objects that did not fit any of these explanations. Objects showing the unusual V-shaped spectral energy distributions, the extreme broad emission lines, the point source morphology, the deep redness, and the absence of X-rays all at once. The objects that had been most puzzling from the beginning remained puzzling. Then, in July 2024, de Graaf's team encountered something extraordinary. Buried in their dataset was a little red dot located approximately 11.9 billion light-years away. Its spectrum was so extreme, so far outside any previously observed range, that the team stopped and stared. They named it the cliff. To understand why the cliff was so significant, it helps to understand in some detail what a Balmer break actually represents physically. Electrons in atoms exist only at specific, discrete energy levels. These are not arbitrary. They are determined by quantum mechanics, and each element has its own unique configuration of allowed energy states. When a photon encounters an electron, it can be absorbed only if its energy corresponds precisely to the difference between the electron's current energy level and a higher one. Photons with the wrong energy pass right through. For hydrogen, the second energy level is particularly important. A photon with a wavelength of 364.6 nanometers carries exactly enough energy to ionize hydrogen from the second energy level, meaning it can strip the electron away from the atom entirely, rather than simply promoting it to a higher bound state. Any photon with a wavelength shorter than 364.6 nanometers has more than enough energy for this ionization and gets absorbed. Any photon with a longer wavelength does not have enough energy and passes through. The result is a sharp discontinuity in the observed spectrum at that wavelength. Below it, the spectrum drops off because those photons are being absorbed. Above it, the spectrum continues relatively normally. This feature is called the Balmer break, and its presence tells astronomers that there is hydrogen gas between the light source and the telescope. The sharpness of the break carries additional information. In a typical galaxy, the break is gradual and smeared because the light is coming from many different stars at different temperatures and passing through hydrogen gas of varying densities. The more uniform and pure the hydrogen atmosphere, the sharper the break appears. A very steep, near-vertical break implies an unusually homogeneous and dense envelope of hydrogen surrounding the light source. The cliff showed a Balmer break roughly twice as strong as any previously observed ancient cosmic object. It was so extreme that the team felt compelled to discard their existing interpretive frameworks and start fresh. The spectral signatures of the cliff were contradictory in a way that was genuinely new. On one hand, the broad emission lines clearly pointed toward an extremely massive, fast-accreting black hole. On the other hand, the steep, sharp Balmer break indicated a dense, relatively uniform sphere of hydrogen gas surrounding the light source, which is a signature more associated with the outer atmosphere of a very young, massive star, a black hole, surrounded by a star-like hydrogen envelope. The object appeared to be both at once. De Graaf proposed a new category for it, a black hole star. The concept, taken at face value, sounds self-contradictory, but it has a coherent physical description. A black hole star would consist of a supermassive black hole at its center, surrounded by an enormous dense sphere of hot hydrogen gas. The outer envelope would not be powered by nuclear fusion, as in ordinary stars. Instead, it would be energized by the black hole at its core, which would be actively consuming gas from the interior of the envelope and converting a fraction of that mass into radiated energy. From the outside, the object would look remarkably like a very large, very hot star. Internally, it would be something fundamentally different. The hydrogen envelope would scatter and reprocess the radiation produced by the black hole. High-energy photons, including X-rays, would be absorbed and re-emitted at lower energies, shifting toward the red and infrared. This would explain the complete absence of detectable X-rays from little red dots. The X-rays are not absent. They are converted into the thermal and optical emission that we actually observe. The dense hydrogen envelope would also produce the steep Balmer break, because it presents an unusually uniform and thick medium of hydrogen to any photons trying to escape. And the black hole at the center, consuming gas at high rates, would power the extreme luminosity and generate the broad emission lines from rapidly orbiting gas in the inner regions of the system. But there were still open questions. Where does the hydrogen envelope come from? And how does such a system form in the first place? The answer to both may lie in a feature of the large-scale structure of the universe that is generally invisible to direct observation. The universe is not distributed randomly. Matter is organized along a vast network of filaments and sheets, separated by enormous voids, forming a structure sometimes described as resembling a cosmic web. Within this web, matter concentrates at intersections and along filaments, and the concentrations of invisible dark matter called halos are the scaffolding around which visible structures form. Dark matter halos have a property that turns out to be crucial in this context. They spin, and the rate at which they spin varies. Most halos rotate at moderate speeds. The centrifugal effect of this rotation tends to spread out the gas and matter inside the halo as it falls inward, forming a disk rather than a compact sphere. This is why most galaxies are disk-shaped, because the gas that formed them was spinning when it collapsed. But a small fraction of dark matter halos spin very slowly. In these low-spin halos, the gas does not spread outward. It remains compact, concentrated, and dense. It falls inward without forming a stable rotating disk. In such environments, the conditions may be just right for black hole stars to form. The gas stays dense enough and remains in close enough contact with the forming black hole to create and maintain the thick hydrogen envelope that characterizes these objects. This picture also offers a potential explanation for why little red dots form where and when they do. In the early universe, shortly after the Big Bang, the conditions for extremely dense, low-spin gas concentrations would have been more common. As the universe expanded and evolved, the structure of the cosmic web changed. The supply of cold, dense gas gradually declined, and the specific combination of factors needed to produce and sustain a black hole star became increasingly rare. This would explain why little red dots appear abundantly between roughly 500 million and 1.5 billion years after the Big Bang, and then disappear. Corroborating evidence came in 2025, when astronomer Rohan Naidu of MIT and his team published a study of an object they also identified as a black hole star. This object had a thick hydrogen gas envelope approximately 40 astronomical units in diameter. which for context means it extended to roughly 40 times the distance between Earth and the Sun. It also showed one of the strongest Balmer breaks ever recorded at any distance in the universe. Naidu's team proposed a model of little red dots as two-component systems. The inner component is the black hole star itself, a massive black hole surrounded by a dense hydrogen envelope, producing the broad emission lines, the extreme Balmer break, the point source light distribution, and the strong red and infrared emissions. The outer component is the host galaxy surrounding it, still actively forming stars, producing narrow emission lines and ultraviolet radiation. When you superimpose the spectrum of the inner black hole star, which is brightest in red and infrared, with the spectrum of the star-forming outer galaxy, which is brightest in ultraviolet, the combined result is a spectrum with high emission at both ends and a relative deficit in the middle. That distinctive V-shape in the spectral energy distribution, which had resisted explanation for so long, emerges naturally from this two-component picture. And the absence of dust? In a black hole star model, the redness does not come from dust at all. It comes from the opacity of the dense hydrogen gas envelope itself. Thick, hot gas absorbs and reprocesses radiation in ways that shift its output toward longer, redder wavelengths. There is no dust shortage, because there never needed to be any dust. The overmassive black hole problem also finds a resolution in this model. The standard method for estimating a black hole's mass from spectroscopic data involves measuring how broad the emission lines are. Broader lines mean faster orbital velocities in the gas around the black hole, and faster velocities imply a more massive central object. But in a black hole star, photons do not travel cleanly outward from the black hole to the observer. They scatter repeatedly through the dense hydrogen envelope. Each scattering event shifts the photon's wavelength slightly, and the cumulative effect of many such events is to artificially broaden the emission lines beyond what the black hole's actual gravity would produce. The black holes look far more massive than they actually are, because the gas they are embedded in distorts the measurement. When researchers applied corrections for this photon scattering effect, the estimated black hole masses dropped substantially, by factors of roughly 100 to 300. After correction, the black hole to galaxy mass ratios fell back toward the expected range of around 0.1%. The overcrowded, oversized black holes were a measurement artifact. The underlying reality was more consistent with what we see in the local universe. The elegance of the black hole star model is that it resolves multiple outstanding problems simultaneously. And with a single physical framework, it explains the redness without requiring impossible amounts of dust. It explains the missing X-rays. It explains the extreme Balmer break. It explains the broad emission lines. And it produces the characteristic V-shaped spectrum through the interaction between the black hole star and its surrounding host galaxy. No other proposed model has managed to account for all of these features at once. What makes the black hole star concept particularly striking is that it was not invented in response to the observations. It was predicted 16 years before Webb detected the little red dots. In 2008, theoretical astrophysicist Mitchell Beagelman at the University of Colorado published a paper proposing a class of object he called quasi-stars. The model described the following scenario. A black hole forms either from stellar collapse or from the direct collapse of a massive gas cloud inside an extremely dense gas envelope. Rather than the envelope dispersing outward as radiation pressure builds, as would happen in a conventional star formation scenario, the envelope remains gravitationally bound. The black hole sits at the center, consuming gas from the interior of the envelope, and the energy released by that accretion flows outward and heats the surrounding gas, which then radiates. From the outside, the object looks like a single enormously massive star. From the inside, it is a black hole with a thick gas atmosphere. Beagelman's model predicted that in this configuration, the black hole could grow at extraordinary rates, potentially reaching thousands of solar masses in just a few million years, far faster than a black hole consuming gas from an external accretion disk. Eventually, the envelope would cool to a temperature floor of around 4,000 Kelvin. At that point, radiation pressure would overcome the gravitational binding of the envelope, and the outer atmosphere would be expelled. The quasi-star phase would end, leaving behind a naked black hole of substantially greater mass than it started with. Beagelman argued that this was not a distinct class of objects but a transient phase, a brief window in a black hole's developmental history lasting perhaps only a few million years. He also speculated that if conditions of extremely high gas inflow were recreated later in the black hole's life, perhaps through a particularly gas-rich merger, similar quasi-star conditions might temporarily reassert themselves. Some black holes might pass through this phase more than once. The little red dots vanish from observations roughly 1.5 billion years after the Big Bang. This timing is consistent with Begelman's prediction that quasi-stars are a brief, early phase that ends when the conditions for dense, compact gas envelopes are no longer met. As the universe continued to expand and the supply of pristine, dense hydrogen in low-spin halos diminished, the conditions necessary to form and sustain black hole stars became increasingly rare. By the time the universe was 1.5 billion years old, those conditions had largely passed. The convergence between a theoretical prediction from 2008 and observational data from the most advanced telescope ever built is striking. Begelman described a hypothetical object. 2 decades later, Webb may be photographing them, but it is important to be precise about the state of the evidence. The black hole star interpretation is the best-fitting explanation for the available data. It is not yet confirmed. The Rubies survey and the analyses by Naidu and others have built a strong case. But there are open questions that the model does not yet cleanly answer. Among the most fundamental, how common is the black hole star phase? If these objects are genuinely present in large numbers across the early universe, they should be detectable in a predictable distribution. But the diversity of objects within the little red dot category revealed by Rubies complicates any simple census. The data suggest that the little red dot population is heterogeneous, containing multiple types of objects, and distinguishing genuine black hole stars from the various other categories requires detailed spectroscopy that is expensive in telescope time. How long does the black hole star phase typically last? Begelman's original estimate was a few million years, which on cosmic timescales is extremely brief. But the actual duration would depend on the mass of the initial black hole, the density and temperature of the surrounding envelope, the rate of gas inflow, and how the system evolves as the black hole grows and its radiation output increases. These are parameters that can in principle be constrained by observations, but the current sample is still too small and too poorly characterized to pin them down. What triggers the formation of the initial black hole inside the gas envelope? The standard pathway to black hole formation, the collapse of a massive star at the end of its life, produces black holes of at most a few tens of solar masses. These are far too small to be the seeds of the supermassive black holes we observe in the early universe, unless they can grow with extraordinary speed. One alternative is direct collapse. A massive cloud of primordial gas, under the right conditions, collapses directly into a black hole without ever passing through a stellar phase. Direct collapse black holes are a well-established theoretical concept, proposed as a potential explanation for the rapid appearance of supermassive black holes in the early universe, but they have never been observationally confirmed. Some researchers have proposed that little red dots might represent the first direct observational evidence of this process. The connection is not yet established, but it is an active area of theoretical and observational investigation. There is also the deeper question of what the apparent disappearance of little red dots tells us about the evolution of the early universe. Objects that were abundant at 600 million years after the Big Bang are gone by 1.5 billion years after. Something changed in the cosmic environment during that window. Whatever conditions enabled black hole stars to form, whether related to gas density, halo spin rates, merger rates, or the overall thermal state of the intergalactic medium, those conditions did not persist. Understanding what changed and why would illuminate an important transitional period in the history of the universe, the epoch when the cosmos shifted from its primordial state to something more closely resembling what we observe today. The broader significance of little red dots connects to one of the longest-standing, unsolved problems in astrophysics, the origin of supermassive black holes. We know that black holes with masses of billions or even tens of billions of solar masses existed less than 1 billion years after the Big Bang. We know that the conventional growth pathway, in which stellar mass black holes gradually accumulate gas over billions of years, cannot produce objects that massive in that shorter time. Something must account for the gap. The black hole star model addresses this problem on 2 fronts. First, the broadening of emission lines caused by photon scattering in the hydrogen envelope has likely caused systematic overestimates of black hole masses in the early universe. Some objects that appeared to require implausibly rapid growth may actually have been smaller, more reasonably sized black holes that appeared more massive due to the properties of their environments. Correcting for this effect reduces the tension between observed masses and theoretical growth predictions. Second, the dense hydrogen envelope surrounding a black hole star creates conditions under which the black hole can potentially bypass its usual growth rate limit. Under ordinary circumstances, a black hole's radiation pushes back against infalling gas, limiting how fast the black hole can feed. This limit is called the Eddington limit. But when the black hole is embedded in a dense envelope whose mass greatly exceeds the black hole's own mass, the effective Eddington limit is calculated differently, based on the total envelope mass rather than the black hole mass alone. This shifts the limit upward, potentially allowing the black hole to grow at rates substantially faster than would otherwise be possible. Together, these two effects, reduced mass estimates from corrected line broadening and enhanced growth rates from the dense envelope environment, ease the tension between observed supermassive black hole masses and theoretical growth models. They do not fully resolve it, but they move in the right direction. The question of how supermassive black holes formed so early is one of the outstanding problems of modern cosmology. The black hole star model and the little red dot observations do not answer it definitively, but they open credible new pathways for investigation and suggest that the answer may lie in physics that was present in the early universe but absent today. One of the most productive things little red dot research could enable is the construction of a detailed life cycle chart for black hole stars, analogous to the Hertzsprung-Russell diagram that maps the evolutionary stages of ordinary stars. For regular stars, we can observe populations at every stage of their development and piece together a coherent picture of how they are born, evolve, and eventually end. For black holes, no such comprehensive observational framework yet exists. Little red dots, if they genuinely represent a distinct and observable phase of black hole evolution, might provide the data needed to start building one, measuring the temperatures, luminosities, envelope sizes, internal dynamics, and host galaxy properties of a large sample of black hole star candidates could, over time, produce a classification scheme and evolutionary model for these objects. That kind of map would have consequences far beyond the little red dot mystery itself. If black hole stars are a necessary phase through which supermassive black holes pass on their way to full size, then understanding this phase would be a key step toward explaining why nearly every large galaxy in the universe today has a supermassive black hole at its center. Why those black holes consistently bear a particular mass relationship to their host galaxies, and what role black holes play in regulating the formation of stars across cosmic time. The fact that an instrument designed and launched by human engineers can peer back nearly 14 billion years in time and identify objects that may represent previously unknown cosmic phenomena is itself extraordinary. The James Webb Space Telescope has already delivered far more surprising results than most of its designers expected, and it is still in the early stages of its operational life. The little red dots were not predicted by anyone working on the telescope's scientific program. They showed up in the data and demanded explanation. That is, in many ways, the most productive mode of scientific progress. Not the confirmation of what we expected, but the encounter with what we did not. The little red dots were invisible to every instrument that preceded Webb. They were there all along, embedded in the ancient light of the early cosmos, waiting for a telescope sensitive enough to detect them and instruments precise enough to begin decoding their nature. What the field now needs is more data, more spectroscopic observations of little red dot candidates, better constraints on their temperatures, densities, sizes, and masses, more detailed modeling of how photons scatter through dense hydrogen envelopes and how that distorts the spectral signatures we observe, observations at wavelengths currently underrepresented in the dataset, and more time, because science of this kind is not resolved quickly. Begelman's 2008 paper waited 16 years before observations appeared that might confirm its central predictions. That is not unusual in astrophysics. Theoretical predictions often precede observational confirmation by years or decades, because building instruments capable of testing them takes time. The Higgs boson was predicted in 1964 and confirmed in 2012. Gravitational waves were predicted by Albert Einstein in 1916 and detected in 2015. The black hole star is a younger prediction, and the field is younger still. But the trajectory feels similar. What makes this moment particularly interesting scientifically is that it is not just a single anomaly that needs explaining. Little red dots are pointing toward a cluster of connected puzzles. The origin of supermassive black holes, the role of direct collapse in early black hole formation, the coevolution of black holes and galaxies, the physics of extreme accretion, and the nature of the transition between the primordial universe and the one we inhabit today. Each of these is a major open question in its own right. The possibility that a single class of objects might provide observational leverage on all of them simultaneously is one of the reasons this research area has generated such intense activity in recent years. Hundreds of papers on little red dots have been published in the last 2 years alone. This is a field in genuine ferment. Interpretations are changing rapidly, sometimes from month to month. The diversity revealed by rubies has complicated clean categorizations. The extreme properties of objects like the cliff are pushing theoretical models to their limits. And the community is still working out the basic taxonomy of what counts as a genuine little red dot and what does not. This is what active frontier science looks like. It is not a story of steady progress toward a predetermined answer. It is a process of accumulating observations, proposing and testing models, finding where models fail, revising them, and gradually converging on a picture that accounts for more and more of what is actually seen. The little red dots are at a very early stage of that process. The black hole star model is the current best candidate, but it is not the final word. Future observations, possibly including data from instruments not yet built, will add detail, resolve ambiguities, and likely reveal new complications that force further revision. What seems clear is that the early universe was doing something we did not predict. Dense, compact, intensely luminous objects powered by some combination of stellar and black hole physics were present in enormous numbers during the first billion years of cosmic history. And then they were gone. Whatever they were part of the story of how the universe we live in came to be. Finding out precisely what they were and what happened to them is one of the most interesting scientific problems currently being pursued. If you find yourself drawn into questions like this, where a single observation opens up into deeper and deeper layers of unknown territory, there is reason to follow along. Science at the frontier moves quickly, and the picture forming around little red dots is likely to look quite different in 5 years than it does today. The questions are real, the evidence is genuinely strange, and the people working on the problem are doing rigorous and careful work under difficult observational constraints. Whatever they find, it is going to be worth knowing. If the ideas in this video sparked something for you, consider subscribing so you catch future explorations of discoveries like this one. The early universe has more surprises waiting. To fully appreciate why the little red dot phenomenon carries so much scientific weight, it helps to understand the instrument that found them and what it took to build it. The James Webb Space Telescope is the most complex scientific instrument ever launched into space. Its primary mirror spans 6.5 meters across, more than 2.5 times the diameter of the Hubble Space Telescope's mirror. But the difference between Webb and its predecessors is not just size. It is the wavelength range it is optimized for. Every telescope is designed to be sensitive to particular portions of the electromagnetic spectrum. Hubble was primarily designed for ultraviolet and visible light, with some capability in the near-infrared. This made it excellent for studying galaxies as they appeared a few billion years ago, but it was not well suited for studying the very first galaxies. There is a fundamental reason for this. The universe is expanding, and light from extremely distant objects has been traveling for so long that its wavelength has been stretched considerably. An object that emitted visible light 13 billion years ago will have its light arrive at Earth in the infrared. If your telescope cannot efficiently detect infrared, you cannot see the earliest structures in the universe. Webb was designed from the beginning to excel in the near-infrared and mid-infrared, specifically to address this limitation. Its detectors are optimized for wavelengths between 0.6 and 28 micrometers, and it operates at a temperature of approximately -233 degrees Celsius, colder than the surface of Pluto, to prevent its own heat from swamping the faint infrared signals it is trying to detect. This thermal management is achieved through a 5-layer sunshield roughly the size of a tennis court, which keeps the telescope permanently shadowed from the sun. Earth and Moon simultaneously. The location where Webb operates, a point in space called the second Lagrange point, roughly 1.5 million kilometers from Earth in the direction away from the sun, was chosen precisely because it allows the sunshield to keep the telescope perpetually cold while maintaining a stable thermal environment. Hubble, by contrast, orbits Earth at just above 500 kilometers altitude, passing repeatedly through Earth's shadow, which creates temperature variations that complicate sensitive observations. Webb's instruments include 4 primary science tools. The near-infrared camera, or NIRCam, is the main imaging instrument and operates as the primary wavefront sensing system. The near-infrared spectrograph, or NIR-SPEC, is capable of simultaneously taking spectra of up to 200 objects in a single observation, using a programmable array of tiny shutters that can be opened and closed individually to select specific targets in the field of view. The mid-infrared instrument, known as MIRI, covers the longer infrared wavelengths and can image objects and obtain spectra in a regime that was essentially inaccessible from space before Webb. And the near-infrared imager and slitless spectrograph, or NIRIS, provides additional imaging and spectroscopic capabilities. It was the combination of NIRCam and MIRI that first revealed little red dots in the Eiger and Fresco surveys, and it was NIRSPEC that allowed the detailed spectroscopic analysis that began to characterize their properties. Without all 3 instruments working in concert, the distinctive signatures of little red dots would either be undetected or uninterpretable. The development of Webb took more than 20 years and involved contributions from NASA, the European Space Agency, and the Canadian Space Agency, along with hundreds of contractors and thousands of scientists and engineers. Its cost exceeded $10 billion. It was launched on Christmas morning 2021 from the Guiana Space Center in French Guiana and reached its final operational orbit around the second Lagrange point in late January 2022. The telescope's commissioning phase lasted 6 months, and routine science operations began in July 2022. In less than 3 years of operations, Webb has delivered results that are transforming multiple areas of astrophysics simultaneously. It has detected galaxies in the very first few hundred million years of cosmic history. It has provided the most detailed atmospheric spectra of exoplanets ever obtained. It has resolved structures in nearby galaxies at unprecedented resolution. And it has found the little red dots. The breadth and pace of discovery from Webb has surprised even its most optimistic advocates. When it launched, most scientists expected it to do its job well and extend what was already known. What it has actually done, repeatedly, is find things that were not expected and cannot be easily explained by existing models. This is not a flaw in the instrument. It is exactly what the most powerful new tools in science are supposed to do. The history of astronomy is a history of unexpected discoveries made possible by new observational capabilities. The discovery of pulsars in 1967 by Jocelyn Bell Burnell came from a new radio telescope at Cambridge University that was sensitive enough to detect rapid periodic signals that previous instruments had missed. The discovery of the cosmic microwave background in 1965 by Arno Penzias and Robert Wilson came from a microwave antenna that was sensitive enough to detect a faint, uniform noise that turned out to be the afterglow of the Big Bang. The discovery of gamma-ray bursts in the late 1960s came from military satellites designed to detect nuclear tests but sensitive to a phenomenon that had nothing to do with weapons. In each case, a new instrument opened a new window, and what was seen through that window was not what anyone had predicted. Little red dots fit this pattern. They were not predicted, they are present in large numbers. They are deeply anomalous, and they are leading researchers toward a class of object, the black hole star that exists in a previously theoretical corner of physics and may resolve several problems at once. Understanding where the concept of a black hole star fits within the broader landscape of known and theorized compact objects requires some context about the diversity of objects that populate the extreme end of the cosmic mass spectrum. Ordinary stars are powered by nuclear fusion. In the cores of stars like the Sun, hydrogen nuclei fuse into helium, releasing energy in the process. The energy output creates an outward pressure that balances the inward pull of gravity. This equilibrium, known as hydrostatic balance, is what keeps a star stable over millions or billions of years. When the fuel runs out, the balance fails and the star collapses. For stars like the Sun, this produces a white dwarf. For more massive stars, the collapse is more violent, resulting in a supernova explosion and leaving behind either a neutron star or a black hole. Depending on the mass of the original star, neutron stars are extraordinary objects. When a massive star collapses, the electrons and protons in its core are compressed together under immense pressure, forming neutrons. The result is an object containing roughly 1 to 2 solar masses compressed into a sphere only about 20 kilometers across. The density is so extreme that a teaspoon of neutron star material would weigh roughly 4 trillion kilograms. Neutron stars are supported against further collapse not by thermal pressure or radiation pressure, but by a quantum mechanical phenomenon called neutron degeneracy pressure, which resists further compression at the quantum level. If the mass of the collapsing core exceeds a certain threshold, neutron degeneracy pressure is not sufficient to halt the collapse, and the object continues collapsing into a black hole. A stellar mass black hole might contain between 5 and a few tens of solar masses compressed within an event horizon, the boundary within which nothing, not even light, can escape. At the other extreme, cite supermassive black holes, which contain millions or billions of solar masses and occupy the centers of most large galaxies. Between these extremes are intermediate mass black holes, which have been observed in some dense star clusters and dwarf galaxies, and which may play a role in the formation of supermassive black holes through mergers. The black hole star, as described by Balmer, and as potentially observed in the form of little red dots, occupies a strange intermediate position. It is not a conventional star because it does not derive its energy from nuclear fusion. It is not a conventional black hole because it is surrounded by a stellar-scale envelope that completely changes its observable properties and its growth dynamics. It is something in between, something that bridges the two categories in a way that conventional astrophysics did not previously have room for. The theoretical concept Balmer proposed in 2008 drew on earlier work in the physics of supermassive star formation. Before the discovery of little red dots, theorists had proposed that the very first stars in the universe, sometimes called population 3 stars, might have been extraordinarily massive by the standards of stars today. Modern star formation is complicated by the presence of heavy elements produced by previous generations of stars. These metals, as astronomers call all elements heavier than hydrogen and helium, allow gas clouds to cool more efficiently, which causes them to fragment into many smaller clumps before collapsing into stars. This fragmentation is why most stars today are relatively modest in mass. The very first stars formed from primordial gas that contained essentially only hydrogen and helium, without metals to facilitate efficient cooling. Early gas clouds may not have fragmented as readily, potentially allowing individual stars to grow to masses hundreds or even thousands of times the mass of the Sun. These hypothetical population 3 stars have never been directly observed, partly because they would have been so short-lived, burning through their fuel in just a few million years, and partly because they would be impossibly faint at the distances we would need to observe them. If population 3 stars existed in the predicted mass range, their collapse would have produced black holes far more massive than anything that forms today. These more massive seeds would have had a head start in the growth race towards supermassive black holes. But even the most optimistic estimates of population 3 star masses fall short of explaining how black holes of billions of solar masses existed so early in the universe. Something more rapid is still needed. Direct collapse is the most extreme of the proposed solutions. In this scenario, under specific conditions, a massive cloud of primordial hydrogen gas collapses directly into a black hole without passing through a stellar phase at all. The conditions required are quite specific. The gas cloud must be massive enough to overcome fragmentation. It must not be able to cool efficiently enough to form stars first, and it must experience infalling gas at a rate high, enough to prevent the kind of gradual buildup that would produce an ordinary stellar sequence. In environments where radiation from nearby star-forming regions dissociates molecular hydrogen, preventing the efficient cooling that would otherwise cause the cloud to fragment, direct collapse becomes more plausible. The cloud stays warm, does not break apart, and can fall inward as a single massive entity. Theoretical models suggest direct collapse black holes could form with initial masses of 10,000 to 100,000 solar masses, giving them a far more substantial head start than the stellar mass seeds produced by conventional stellar evolution. If black hole stars form in the aftermath of direct collapse events, the picture might unfold as follows. A massive gas cloud in a low-spin dark matter halo collapses directly into a black hole with a mass of tens of thousands of solar masses. The surrounding gas, rather than dispersing, remains bound because of the slow spin of the halo. The black hole quickly accretes the inner envelope, and the energy released heats the outer envelope, creating the characteristic structure of a black hole star. In this phase, the black hole grows rapidly, potentially by orders of magnitude over a few million years. When the envelope finally disperses, a much more massive naked black hole remains, which then continues to grow more slowly through conventional accretion. Run this process across a large population of objects in the early universe, and you begin to see how supermassive black holes might have assembled themselves in time. Not through slow, steady, billion-year accretion, but through brief, intense episodes of rapid growth during the black hole star phase, followed by longer periods of more conventional evolution. The convergence of observational and theoretical progress on this problem is happening at an unusual pace. Normally, it takes years or decades for a new observational discovery to be connected to a theoretical prediction, and for that connection to be tested and refined. The black hole-star connection has developed remarkably quickly, partly because Webb data is being processed and published at an extraordinary rate, and partly because the theoretical groundwork was already laid by Begelman's 2008 paper and subsequent work on direct collapse and quasi-star physics. The pace of publication in this field has itself become notable. In the 2 years following the first detailed characterization of little red dots, hundreds of papers were submitted to the Astrophysics preprint server. Researchers across multiple institutions on multiple continents are working on overlapping aspects of the problem simultaneously, and the results are sometimes in tension with each other. This is not unusual for a field in active development, but the speed and volume of output is particularly striking, one of the productive tensions in the air. Current literature is between studies that support the black hole star interpretation and studies that argue for alternative or modified explanations. Some researchers have proposed that little red dots might be explained by extreme dust geometries that have not yet been adequately modeled. Others have suggested that unusual stellar populations with non-standard initial mass functions might account for some of the anomalies. Still others have proposed that the objects might involve multiple overlapping components that cannot yet be spatially resolved, given their enormous distances. The scientific process requires these competing explanations to be rigorously evaluated against each other. A model that elegantly explains several observations simultaneously is scientifically attractive, but elegance is not confirmation. The black hole star model needs to make specific, testable predictions that can be checked against future observations. And it needs to successfully account for the full diversity of little red dot properties, including the subpopulations that seem to deviate from the typical pattern. One of the most important near-term developments would be the detection of X-ray emission from objects currently classified as little red dots. In the black hole star model, the absence of X-rays from these objects is explained by absorption and reprocessing within the dense hydrogen envelope. But this is a testable prediction. If the black hole star phase ends when the envelope disperses, then the naked black hole left behind should eventually become an X-ray source. If astronomers can identify objects that appear to be transitioning out of the little red dot phase, they might be able to catch the X-ray emission turning on. Future X-ray observatories with greater sensitivity than current instruments would be essential for this kind of test. The proposed next-generation X-ray telescope, LINX, if funded and built, would have the sensitivity to detect X-ray emission from black holes at the distances of little red dots, even if the emission is partially absorbed. Combined with continued infrared spectroscopy from Webb, this would allow a much more complete physical picture of these objects. Radio observations offer another avenue. Some models of accretion onto rapidly feeding black holes predict the production of jets, narrow beams of material and energy launched from the poles of the accretion system. These jets produce radio emission, and their presence or absence would constrain models of the accretion physics inside black hole stars. The NGVLA, the next-generation Very Large Array being developed for the coming decade, would have the sensitivity to detect radio emission from sources at little red dot distances. There is also the prospect of gravitational wave observations. When two black holes merge, they produce gravitational waves that carry information about the masses, spins, and orbital parameters of the merging pair. The LISA mission, the Laser Interferometer Space Antenna planned for launch in the early 2030s, is designed to detect gravitational waves from merging supermassive and intermediate mass black holes. If black hole stars are the precursors to supermassive black holes, and if those supermassive black holes undergo mergers, LISA will detect those mergers, and the masses involved will test the predictions of the black hole star growth model. The idea of linking infrared spectroscopy from Webb, X-ray data from future observatories, radio data from the Next Generation Very Large Array, and gravitational wave data from LISA into a coherent multi-messenger picture of black hole formation and growth is one of the most ambitious goals in contemporary astrophysics. Little red dots sit at the center of this convergence. They are the observational anchor around which these different lines of inquiry can be organized. The broader context for all of this work is a field that is undergoing rapid transformation. The past decade has seen the first direct detection of gravitational waves from merging black holes and neutron stars. It has seen the first direct imaging of a black hole's event horizon shadow by the Event Horizon Telescope. It has seen the discovery of dozens of high redshift quasars, representing supermassive black holes existing less than 1 billion years after the Big Bang. And now it is seeing the emergence of a potential new class of cosmic object that may link several of these threads together. There is something philosophically interesting about the fact that the objects most relevant to understanding the largest structures in the universe, the supermassive black holes at the centers of every large galaxy, may be best studied not by looking at familiar nearby examples, but by finding their counterparts in the most distant and ancient parts of the observable cosmos. The early universe is, in a meaningful sense, a laboratory. The conditions that existed then, the high densities, the abundance of pristine hydrogen, the prevalence of low-spin halos in specific environments, are conditions that no longer exist today. We cannot recreate them. We can only observe them across a distance so vast that the light we are seeing left its source before the Earth existed, before the Sun existed, before most of the stars in the Milky Way had formed. That light has been traveling for over 13 billion years. It passed through regions of the universe that have since been restructured by billions of years of stellar evolution, galaxy formation, and large-scale gravitational dynamics. When it finally arrives at the detectors aboard the James Webb Space Telescope, it carries information about a state of the universe that is otherwise inaccessible. The little red dots are windows into that state. Whatever they turn out to be, precisely, the fact that we can find them, characterize them, and begin to understand them is a testament to the cumulative achievement of generations of scientists and engineers who built the tools and frameworks necessary for this kind of observation. The physics being applied to interpret little red dot spectra draws on quantum mechanics developed in the first half of the 20th century. Nuclear and atomic physics refined over decades of laboratory experiment, observational techniques pioneered across generations of ground and space-based astronomy, and theoretical frameworks for black hole physics that go back to Carl Schwarzschild's solution of Einstein's field equations during the First World War. Science is cumulative. Every discovery depends on a foundation of prior work. The little red dot story is the latest chapter in a very long narrative, and it is being written in real time by hundreds of researchers working on different pieces of a puzzle whose full shape is not yet visible. What we can say with confidence is this: the James Webb Space Telescope found something unexpected in the ancient light of the early cosmos. That unexpected finding is pointing toward a class of object that was theoretically predicted but never observed. And that class of object, if the current interpretation holds, would help resolve one of the deepest mysteries about how the universe came to look the way it does. The supermassive black holes at the centers of galaxies, including the one at the center of our own Milky Way, may owe their existence in part to a brief, intense phase of growth that we are now, for the first time, able to observe directly. The story is not finished. It may be years or decades before the full picture is clear, but the direction of the evidence is compelling. The theoretical framework is surprisingly well developed, and the instruments available to continue the investigation are the most powerful ever built. The universe has been keeping this secret for 13 billion years. We are only just beginning to hear it. To properly situate the little red dot discovery, it helps to walk through the history of how our understanding of the early universe has developed. Because the surprises Webb is delivering are surprises relative to a model that itself took decades to assemble. The idea that the universe had a beginning, that it originated in a hot, dense state and has been expanding ever since, was not accepted overnight. In the early 20th century, most scientists assumed the universe was static and eternal, existing more or less as it always had. Albert Einstein himself, when he derived the equations of general relativity in 1915 and 16, found that they implied a dynamic universe, one that was either expanding or contracting. He found this result uncomfortable and introduced a term into his equations, the cosmological constant. specifically to cancel out the expansion and produce a static solution. He later called this the biggest blunder of his career. The observational evidence for an expanding universe came in the 1920s, primarily through the work of Edwin Hubble at the Mount Wilson Observatory in California. Hubble measured the distances to galaxies using a type of variable star called a Cepheid, whose intrinsic luminosity cycles predictably over time, and can therefore serve as a calibrated standard candle for distance measurement. He found that virtually all galaxies were moving away from the Milky Way, and that the more distant a galaxy was, the faster it was receding. This relationship, now called Hubble's law, implied that the universe was expanding in all directions simultaneously. An expanding universe, run backward in time, implied a past state in which everything was compressed into a much smaller volume. In the 1940s, George Gamow, Ralph Alpha, and Robert Herman developed the mathematical framework for what this hot, dense early state would look like. They predicted that the early universe would have been opaque, filled with plasma so hot and dense that photons could not travel freely, bouncing continuously off the ionized gas. As the universe expanded and cooled, eventually the temperature would drop low enough for electrons and protons to combine into neutral hydrogen atoms. This moment, called recombination, would have happened approximately 380,000 years after the Big Bang, and it would have released the photons that had been trapped in the plasma, allowing them to stream freely for the first time. Those photons have been traveling ever since. Stretched by the expansion of space over 13.5 billion years, they have cooled to a temperature of just 2.7 degrees above absolute zero, and now fill the sky as a faint glow of microwave radiation detectable from every direction. This is the cosmic microwave background, the oldest light we can detect. A snapshot of the universe, as it was 380,000 years after its origin. Penzias and Wilson detected the cosmic microwave background in 1965, initially thinking the signal might be noise or interference from pigeon droppings in their antenna. Their inadvertent discovery confirmed the hot Big Bang model and earned them the Nobel Prize in 1978. The detailed mapping of the cosmic microwave background by satellite missions including COBE, WMAP, and Planck has since provided a precise picture of the density fluctuations in the early universe, the seeds of all the large-scale structure we see today. After recombination, the universe entered a period called the Cosmic Dark Ages. Neutral hydrogen gas-filled space. There were no stars yet, and the universe was transparent but empty of luminous objects. This dark age lasted until roughly 100 to 200 million years after the Big Bang, when the first stars began to form. These first stars, the hypothetical population 3 objects mentioned earlier, would have been massive, short-lived, and intensely bright. Their ultraviolet radiation would have begun the process of reionizing the surrounding neutral hydrogen gas, a process that completed over the next several hundred million years and fundamentally changed the properties of the intergalactic medium. The epoch of reionization, roughly between about 200 million and 1 billion years after the Big Bang, is the period when the universe transitioned from being mostly neutral hydrogen to being mostly ionized plasma again. But this time as a result of radiation from stars and active galactic nuclei, rather than from the heat of the early universe. Understanding the sources of reionization, how much energy they produced, what their demographics looked like, and how they interacted with the surrounding intergalactic medium, is one of the central goals of observational cosmology. Little red dots exist squarely within this epoch. At 600 million to 1.5 billion years after the Big Bang, the universe was still in the late stages of reionization. The objects that populate this era are the very sources whose radiation helped transform the universe from an opaque fog of neutral gas into the transparent, structured cosmos we inhabit today. Understanding what those objects were is not just a curiosity. It is central to understanding how the universe came to be habitable for complex structures like galaxies and, ultimately, planets and life. The James Webb Space Telescope was specifically designed to study this epoch. Its infrared capabilities allow it to detect the red-shifted light of objects in the first billion years after the Big Bang. The little red dots are among the most numerous and surprising objects it has found in this era, and their properties are now deeply entangled with questions about reionization, black hole formation, and galaxy evolution during the cosmic dawn. One of the most important things Webb has revealed about the early universe is that it was more structured and more evolved than models predicted. Galaxies that were expected to be small, irregular and chaotic at 600 million years after the Big Bang, are sometimes surprisingly well developed. Some show signs of disk-like structure. Some have already quenched their star formation, meaning they stopped forming new stars at an unexpectedly early time. And the little red dots, whatever they are bright enough and numerous enough to potentially have contributed significantly to the rionization of the intergalactic medium. This last point is worth developing. Rionization was powered by ultraviolet photons produced by hot stars and active galactic nuclei. The question of which source type contributed more is still debated. If little red dots contain rapidly accreting black holes, they would have been producing large amounts of ionizing radiation in this epoch. If they contain dense populations of hot young stars, the same would be true. Either way, the number density of little red dots, suggested by Webb observations, implies that they may have been a significant contributor to the rionization budget, but the V-shaped spectra of little red dots pose a complication for this calculation. The ultraviolet emission from these objects, produced by the star-forming host galaxy in the black hole star model, might be partially or fully absorbed before it escapes into the surrounding intergalactic medium. If the dense hydrogen envelope of the black hole star traps most of the ionizing photons and converts them to lower energy emission, then little red dots might be far less effective at reionizing the universe than their raw luminosities suggest. Resolving this question requires understanding the geometry and opacity of the envelope in detail, which is still ongoing work. The connection between little red dots and rionization also highlights a broader principle of cosmological research. The early universe is a system in which everything is connected. The formation of the first stars, the growth of the first black holes, the evolution of the first galaxies, and the rionization of the intergalactic medium are not independent processes. They regulate each other through feedback mechanisms involving radiation, gas dynamics, and gravity across enormous scales. Understanding any one of these processes in isolation is insufficient. The picture only becomes coherent when all the pieces are considered together. This is why large spectroscopic surveys like Ruby's are so valuable. They do not just characterize individual objects. They provide statistical samples that reveal the distribution of properties across populations. When de Graaf and her team found that the little red dot category contained multiple distinct types of objects, they were doing something fundamental. They were mapping the heterogeneity of the early universe's extreme objects. That map, even in its current incomplete state, constrains theoretical models in ways that individual spectacular cases cannot. The cliff, the extreme little red dot with the sharpest Balmer break ever observed, is scientifically important partly because of its own intrinsic properties and partly because it forced the construction of a new framework, the black hole star model, that could account for it. But the black hole star model's validity as a general explanation for the puzzling subpopulation of little red dots depends on whether it can account for the statistical distribution of properties across the full sample, not just the most extreme individual case. This is the next stage of the analysis, and it is work that will require more data and more careful modeling. The broader context for all of this, observational activity, is a generation of scientists who grew up knowing that the early universe was inaccessible and are now, for the first time in history, able to study it directly. The theoretical machinery for understanding the Big Bang, the formation of large-scale structure, and the evolution of galaxies has been developed over decades, largely in the absence of direct observational constraints from the epoch these theories were meant to describe. Webb is now providing those constraints in real time, and in many cases the constraints are revealing that the theory was incomplete. This is a normal and healthy part of scientific progress. Theories that are developed in the absence of data make predictions that are later tested and sometimes found to be wrong. The fact that Webb's observations of the early universe are surprising does not mean the underlying physics is fundamentally mistaken. It means that the models were built with incomplete information and are now being refined. The standard model of cosmology, grounded in the Big Bang, cold dark matter, and dark energy, remains intact. What is being revised are the astrophysical details of how stars, galaxies, and black holes formed and evolved within that framework. The history of cosmology offers many examples of this kind of revision. The discovery that the expansion of the universe is accelerating, announced in 1998 and attributed to a form of energy called dark energy, required substantial modification to models that had assumed the expansion was decelerating. The discovery that the large-scale structure of the universe resembled a cosmic web of filaments and voids, rather than a more uniform distribution, required major updates to models of structure formation. The discovery that reionization was extended and complex rather than sharp and instantaneous required new models of the sources and topology of ionizing radiation. In each case, the revision made the overall picture more accurate and more detailed, even though it required acknowledging that the previous version was incomplete. The little red dots are following a similar pattern. They are not overturning cosmology. They are adding detail and nuance to our understanding of how the earliest structures formed, how rapidly black holes grew in the cosmic dawn, and what kinds of objects populated the universe during its most transformative early phase. The addition of the black hole star as a genuine physical entity, if confirmed, would enrich the taxonomy of cosmic objects and provide new tools for understanding processes that were previously opaque. Consider what it would mean concretely to have a well-characterized life cycle for black hole stars. Right now, the formation of supermassive black holes is one of the least constrained areas of astrophysics. We observe supermassive black holes at the centers of galaxies. We know they were already very massive early in the universe's history. We have theoretical models for how they might have grown that quickly, involving direct collapse, rapidly accreting quasi-stars, or hierarchical mergers. But we have very little direct observational evidence that distinguishes between these models. If black hole stars are the observational counterpart of Beagleman's quasi-stars, and if they can be characterized well enough to map their evolutionary stages, that would give us a direct window into the growth history of supermassive black holes. We would be able to observe the process in action, rather than inferring it from the endpoints. We would be able to measure growth rates, envelope properties, and the mass distribution of seeds and mature objects, and compare these measurements directly to the predictions of different theoretical models. This kind of direct observational constraint is exactly what the field has been missing. It is worth emphasizing just how unusual this situation is in the history of astrophysics. The formation of most types of objects that we study, from ordinary stars to galaxy clusters, takes place over timescales of millions to billions of years. We cannot watch a star form in real time. We can study objects at different stages of their evolution and piece together a sequence, and we can do detailed theoretical modeling to understand the physics. But we cannot observe the full process from beginning to end. For black holes, the situation is even more extreme.
The events relevant to black hole formation and early growth happened billions of years ago.
We have no direct record of them, except the ancient light that has been traveling toward us ever since. The little red dots are that direct record. They are the preserved image of black hole formation in action, captured in the infrared light that left these objects roughly 13 billion years ago and has been traveling toward us ever since, only now detectable with an instrument sensitive enough to receive it. The James Webb Space Telescope is, in a very real sense, a time machine. It does not send us back in time. It allows us to receive information from a time that, for all practical purposes, no longer exists and can never be revisited. What it shows us is irreplaceable. The fact that the information is coming back surprising, that the early universe looks different from what was predicted, is not a cause for alarm. It is a cause for excitement. Every unexpected result is a potential window into new physics, new processes, or new structures that were present in the universe's history but have not been incorporated into our models. The obligation of the scientific community is to take those results seriously, test them rigorously, and revise the models accordingly. That work is happening now, across dozens of research groups, using data from Webb and from a growing collection of complementary instruments. The picture of little red dots will sharpen considerably over the next few years as more observations are obtained, more spectra are analyzed, and more theoretical models are compared against the data. The question of whether black hole stars are genuinely confirmed as a new class of cosmic object, or whether some other explanation ultimately prevails, will be answered not by argument, but by evidence. There is one more dimension of this story that deserves attention, and that is the human dimension of how science of this kind gets done. The little red dot mystery has been worked on by researchers across multiple continents, multiple institutions, and multiple generations of scientific training. The survey programs that found them were designed by teams who had to argue for telescope time in competitive proposal processes. The theoretical models that are being applied to interpret them were developed by physicists who spent years working on problems that seemed abstract and disconnected from observation. The instruments that made the observations possible were built by engineers who solved problems that had never been solved before, under budgetary and schedule pressures that required extraordinary ingenuity. Jorrit Matthey, who authored the paper that formally categorized little red dots, was working with data from a survey that had been designed to hunt for something else. Anna de Graaf, who designed the Ruby survey and identified the cliff, built her program specifically to pursue anomalous objects after the initial little red dot reports made clear that something unexpected was in the data. Mitchell Begelman, whose 2008 paper predicted quasi-stars, was working on theoretical problems in accretion physics that had no obvious connection at the time to what Webb would observe 16 years later. Rohan Naidu's team at MIT was studying a specific object and found that it fit the black hole star description. This is how science actually works. It is not a linear march toward predetermined answers. It is a network of interconnected efforts, often working at cross purposes or in parallel without full knowledge of each other, gradually converging on a coherent picture through the accumulation of data, the clash of interpretations, and the gradual elimination of alternatives that fail to account for the evidence. The little red dot story is particularly vivid because it is happening so quickly and publicly. The preprint culture of modern astrophysics means that results are available almost immediately upon completion, before formal peer review, and the community can engage with them in real time. This accelerates the rate of progress, but also means the public conversation about these discoveries is happening while the science is still fluid. Interpretations that seem compelling today may be revised tomorrow when new data arrives. This is not a sign of unreliability. It is a sign that the field is genuinely active and that the practitioners are engaging seriously with challenging new evidence. For anyone following this story from outside the professional research community, the appropriate stance is one of engaged curiosity combined with appropriate patience. The headline that Webb found mysterious red dots is accurate. The suggestion that these might be black hole stars, a new kind of cosmic object, is a serious scientific proposal supported by meaningful evidence. The broader implication that understanding these objects could illuminate the origin of supermassive black holes is well-grounded in the reasoning of researchers who have spent careers studying the early universe. But the story is not finished. The science will continue to develop. New observations will add detail. New analyses will test the model. The picture will sharpen, and there will almost certainly be additional surprises, because the universe has so far shown no sign of being simpler than the most complex model we can imagine. The little red dots are a reminder of something that is easy to forget in an era of sophisticated simulation and detailed modeling. The universe does not read our textbooks. It does what it does according to physical laws that we have only partially understood, operating over scales and timescales that are difficult to conceptualize, producing structures and phenomena that lie beyond the range of what any finite human imagination could predict in advance. Our job, as a species that has developed the extraordinary capacity for scientific inquiry, is to look, to measure, to think, and to revise what we think we know when the looking and measuring demands it. The James Webb Space Telescope is doing the looking and measuring at a level of depth and precision that was not possible before. What it is finding in the ancient cosmos is teaching us things about our origins and our place in the universe that could not have been known any other way. The little red dots are a small but vivid example of that process, whatever they ultimately turn out to be, and the evidence is pointing strongly towards something genuinely new. Their discovery will have been a productive chapter in the long story of humanity trying to understand the universe it finds itself in. That story is far from over. In some ways, it is just beginning. The next decade of observations from Webb, combined with new instruments now under construction and new generations of researchers now entering the field, will fill in details that we cannot currently imagine. The questions being asked about little red dots today will evolve into more refined questions, and those questions will evolve into others, in the recursive, iterative way that science always moves forward. What we can say with confidence today is that the early universe was doing something unexpected, that the James Webb Space Telescope has given us the first real look at what that something might be, and that the answer, when it comes, will matter for our understanding of how everything we see around us came to exist. That is enough reason to keep watching, and enough reason to be grateful that the instruments and the ingenuity exist to make these observations possible. There is a dimension of the black hole star problem that connects it to some of the deepest questions in fundamental physics, beyond just the observational astrophysics of the early universe. The behavior of matter under the extreme conditions inside a black hole star, and the physics governing the boundary between stellar and black hole regimes. touches on areas of research that remain genuinely unresolved at a theoretical level. Black holes are among the most extreme objects in the universe, not just because of their mass and density, but because they represent a boundary where our standard descriptions of physics break down. General relativity, Einstein's theory of gravity, describes black holes precisely in terms of their external properties, mass, spin, and charge, but says nothing coherent about what happens inside the event horizon. Quantum mechanics, which governs the behavior of matter at the smallest scales, has its own set of tools that do not straightforwardly apply to the macroscopic geometry described by general relativity. The unification of these two frameworks into a consistent theory of quantum gravity is one of the major unsolved problems of theoretical physics. For practical astrophysics, this unresolved tension is usually not an issue. Black holes can be studied observationally from outside, and the region near but outside the event horizon, where accretion physics operates, is well described by general relativity combined with magnetohydrodynamics and radiation transport. The internal structure of the black hole itself is irrelevant to most astrophysical questions, but black hole stars probe a regime that is, in some ways, adjacent to these deep questions. The interaction between the extreme gravity of the central black hole and the dense, radiation-dominated envelope surrounding it involves physics that is computationally challenging and analytically complex. The way photons scatter through the dense envelope, the dynamics of the boundary between the black hole's sphere of influence and the outer stellar atmosphere, and the stability of the quasi-star configuration, over time all require detailed calculation in a regime where simple approximations failed. Begelman's original 2008 paper made predictions that depended on specific assumptions about these physical processes. Some of those assumptions have since been refined by follow-up theoretical work. But the full computational treatment of a black hole star, including three-dimensional hydrodynamics, radiation transport, magnetic fields, and the self-consistent evolution of the system over millions of years, remains a formidable challenge. The simulations that would be needed to thoroughly test the model against the Ruby's data are at or beyond the frontier of current computational capability. This is another reason why the field is moving as quickly as it is. Observational constraints from Webb are pushing theorists to work harder and faster on models that had been somewhat theoretical curiosities before the data arrived. The little red dots have transformed the black hole star from an interesting theoretical prediction into a pressing observational puzzle that demands rigorous modeling. Resources, both computational and intellectual, are being directed toward it in a way that would not have happened without the Webb observations to motivate the effort. There is also a dimension of this story that connects to the ongoing effort to measure fundamental cosmological parameters with increasing precision. The standard cosmological model, often referred to as lambda CDM for the cosmological constant that represents dark energy and cold dark matter, is described by a set of parameters including the Hubble constant, the density of matter and dark energy, the amplitude of primordial density fluctuations, and others. These parameters are constrained by multiple independent observations, including the cosmic microwave background, the large-scale distribution of galaxies, the properties of galaxy clusters, and measurements of standard candles and standard rulers at various distances. In recent years, attention has emerged in measurements of the Hubble constant, the rate at which the universe is expanding today. Measurements from the early universe, primarily from the cosmic microwave background, give a value of approximately 67 kilometers per second per megaparsec. Measurements from the local universe, using Cepheid variable stars and type Ia supernovae as standard candles, give values closer to 73 kilometers per second per megaparsec. The discrepancy is statistically significant and has persisted despite extensive effort to identify and correct for systematic errors. This Hubble tension, as it is known, suggests either that there are unidentified systematic errors in one or both sets of measurements, or that the standard cosmological model is missing something. Some theorists have proposed modifications to early universe physics, such as a brief period of additional energy density, called early dark energy, that could reconcile the two values. Others have proposed modifications to the late universe physics governing how standard candles are calibrated. The connection to little red dots is indirect but potentially significant. If the population of objects in the early universe is substantially different from what models predict, there could be effects on the evolution of the intergalactic medium, the distribution of reionizing photons, and the thermal history of the gas that eventually forms galaxies. These effects might, in principle, influence the precise value of observables that are used to constrain the Hubble constant from the early universe. The little red dots are not causing the Hubble tension, but their existence is a reminder that our model of the early universe still has gaps. And those gaps could potentially be relevant to fundamental parameter estimation. More directly, Webb observations of the early universe are providing new measurements of distances and expansion rates that will help sharpen our understanding of cosmic history. The most precise measurements of cosmological parameters from the cosmic microwave background come from the Planck satellite, which operated from 2009 to 2013. Webb is not primarily a cosmological parameter measurement machine, but the detailed data it provides on the demographics of early universe objects, including little red dots, contributes to our overall model of how structure formed and evolved, which in turn constrains the cosmological parameters that govern that evolution. One of the most striking things about the current moment in astrophysics is the degree to which different research programs, often developed independently with different primary goals, are converging on common problems from different directions. The Hubble tension is being investigated by researchers studying supernovae, Cepheids, strong gravitational lensing, and the cosmic microwave background. The supermassive black hole formation problem is being approached through direct imaging, spectroscopy, gravitational wave detection, and theoretical modeling. The epoch of reionization is being studied through Lyman alpha-emitting galaxies, quasar absorption spectra, radio observations of neutral hydrogen, and the cosmic microwave background polarization signal. Little red dots sit at the intersection of several of these programs simultaneously. They are present during the epoch of reionization and may have contributed to it. They appear to contain rapidly growing black holes that are directly relevant to the supermassive black hole formation problem. They are found through infrared spectroscopy of the early universe, using the same instruments that are providing new distance measurements relevant to the Hubble tension. And their existence, if confirmed as a new class of object, would need to be incorporated into the comprehensive models of cosmic evolution that underlie parameter estimation. This interconnectedness is a feature of modern astrophysics more broadly. The universe is a single physical system. Understanding any part of it deeply requires understanding how it connects to the rest. The little red dots are a new node in this web of interconnection, and tracing the threads that run from them to the rest of what we know about the cosmos is one of the most productive research programs currently underway. The young researchers entering the field today are inheriting problems that are far more complex and far better constrained than those faced by previous generations. They have access to data from the most powerful instruments ever built. They have computational tools that allow them to simulate the universe at scales and resolutions that were unimaginable 20 years ago. And they are benefiting from decades of accumulated theoretical and observational work that gives them a sophisticated framework within which to interpret what they find. At the same time, they are entering a field full of genuine open questions, surprises, and mysteries. The little red dots are one of many examples of how much remains to be discovered and understood even in an era of extraordinary observational capability. The fact that Webb found something so puzzling so quickly in one of the primary target epochs it was designed to study suggests that the early universe is considerably stranger and more complex than we had assumed, and that the work of understanding it is not close to complete. For anyone who finds the large questions captivating, the questions of how the universe began, how it evolved, how the structures we see around us came to be, and what role processes like black hole formation and galaxy evolution played in shaping the cosmos we inhabit, there has never been a better time to be paying attention. The data is flowing, the discoveries are real. The questions are genuinely open, and the answers when they come will matter. If this kind of frontier science is something you want to keep up with, there is no shortage of ways to stay connected. The preprint server at arxiv.org is where most astrophysics papers appear before formal publication, often within days of completion, and many researchers write accessible summaries for general audiences when their results are particularly significant. Popular science writing in this area has also improved substantially, with careful journalists translating complex results for non-specialist readers without sacrificing the essential accuracy of what is being reported. The little red dot story will continue to develop over the coming years. Webb has years of operational life ahead of it, and the observational programs targeting little red dots and related objects are still ramping up. Naidu's team, de Graaf's team, and many others are working on new observations and new analyses. Beagleman, whose theoretical prediction appears to have anticipated something real, is surely watching the data with considerable interest. The theoretical community is actively developing the computational tools needed to model black hole stars in sufficient detail to make precise predictions that can be tested against observations. What you are witnessing, if you are following this story, is science in the process of making a significant discovery, one that may not be fully resolved for years, but that is already changing how researchers think about the early universe. That is a rare privilege because most of the time, science's most important advances are only recognizable in retrospect. Here we can watch the process in something close to real time. The ancient light from these mysterious objects, having traveled for more than 13 billion years through an expanding and evolving universe, has arrived at the most sensitive telescope ever built and told us something we did not know. The work of understanding what it is telling us has only just begun. Science moves forward, not because we already know the answers, but because instruments like Webb, built by thousands of people over decades, keep extending our vision into regions we could not previously reach. In that extended vision, we find the universe doing things we did not predict, forcing us to think harder, model more carefully, and question more rigorously. Little red dots are exactly that kind of discovery, a gift from the ancient cosmos to the curious minds of the present. Whatever they turn out to be, they have already changed the conversation about how the universe began to look the way it does. If this video added something to your understanding of the cosmos, a subscription means you will be there for the next discovery too. The questions raised by little red dots will not disappear, even if the black hole star interpretation turns out to need revision. Why does the early universe contain so many compact, intensely luminous objects? Why do they vanish? Why do the black holes inside them appear overmassive relative to their host galaxies? Why is there no X-ray emission? Why is the Balmer break so steep in some of them, steeper than anything previously measured? These are real observational facts, and any viable model must account for all of them simultaneously. The field will not rest until it does. That is both the discipline and the promise of science. The universe has been here for 13.8 billion years. Humanity has been doing systematic science for only a few centuries. In that tiny sliver of cosmic time, we have gone from not knowing the Earth orbits the Sun to building a telescope that can photograph objects that existed when the universe was less than 1/20th of its current age. The little red dots were waiting in that ancient light the whole time, invisible to everything we had built until now. They are still there, every night, encoded in the faint infrared signals reaching the Webb telescope's detectors in the cold dark beyond the moon. And in the years ahead, the people studying them will piece together what they mean. It is worth pausing for a moment on a number. The light we are analyzing from the little red dots left its source approximately 13 billion years ago. The universe at that time was not the universe we know. There were no planets. There were no second-generation stars enriched with the heavy elements that make rocky worlds possible. The intergalactic medium was still in the process of being reionized by the first burst of ultraviolet light from the first luminous objects. The large-scale structure of galaxy clusters and filaments that defines the present-day cosmic web was only beginning to emerge from the slight density fluctuations imprinted during inflation. We are not looking at a past version of the familiar universe. We are looking at a fundamentally different state of reality, one that existed for a brief window in cosmic time and then transformed irreversibly into the universe that eventually gave rise to stars like the Sun, planets like Earth, and the particular arrangement of matter that became curious enough to point a telescope at its own origins. The little red dots are part of that transformation. They are relics of a phase when conditions were extreme, when dense gas could form structures unlike anything that exists today, and when the seeds of the largest gravitational structures in the present-day universe were being planted. Every supermassive black hole currently sitting at the center of a galaxy, including the 4 million solar mass object called Sagittarius A star at the center of the Milky Way, has a history that traces back to those first hundreds of millions of years. The little red dots may be the first direct observation of the earliest chapters of that history. That is what makes them so significant, and that is why the effort to understand them is so worthwhile. The James Webb Space Telescope is one of the most consequential scientific instruments ever built. To understand why, consider what it replaced and what it enables. Hubble, its predecessor, was a revolutionary instrument that transformed our understanding of the universe across its nearly 35 years of operation. But Hubble was fundamentally limited by its wavelength coverage and its mirror size. Webb's mirror is more than 6 times larger by area, and its detectors are optimized for the infrared wavelengths that carry information from the most distant and ancient parts of the universe. These two differences combine to make Webb not just an improvement over Hubble, but a qualitatively different kind of instrument capable of answering questions that Hubble could not even pose. The investment in Webb has already returned discoveries of fundamental importance, and the telescope is expected to remain operational well into the 2030s, potentially until 2040 or beyond with proper maintenance. In those remaining years, it will continue to accumulate data on little red dots, on the epoch of reionization, on the first galaxies, and on the many other targets that make up its scientific program. The field will be very different in a decade. The picture of the early universe will be far more detailed, far more constrained, and in ways we cannot yet predict, far more surprising. That is the nature of frontier science, and it is one of the most enduring reasons to find it compelling.